To understand the mechanical necessity of this field, we must confront the von Neumann bottleneck, the structural flaw that exists in every computer you have ever used. In a standard architecture, the processor, CPU, and the memory, RAM, are physically separate. Every time the computer performs a task, it must shuffle data back and forth across a narrow bus. This movement is slow, it consumes the vast majority of a system's energy, and it creates a literal traffic jam for information. Neuromorphic computing is the radical attempt to build chips that mirror the biological architecture of the human brain, where processing and memory exist in the exact same physical space, the synapse. The human brain is the most efficient computer in the known universe, capable of performing roughly an exaflop of operations while consuming only about 20 watts of power, less than a dim light bulb. A modern supercomputer attempting the same feat would require megawatts of power and a dedicated cooling plant. Neuromorphic chips such as Intel's Loihi or IBM's True North achieve this efficiency by replacing traditional clocked logic with spiking neural networks, SNNs. In a standard chip, transistors are constantly switching and consuming power at every tick of the clock. In a neuromorphic chip, the neurons only fire or spike when they receive enough input signal. If there is no data to process, the chip is effectively silent. This event-driven nature means that power consumption scales with activity, not with clock speed, leading to energy efficiency gains of several orders of magnitude. For the DevOps and hardware R&D world, the rise of neuromorphic computing represents the next frontier of edge AI. Right now, running a massive large language model, LLM, requires a massive server rack with high-end GPUs. This is fine for the cloud, but it is impossible for a drone, an autonomous vehicle, or a remote sensor that needs to operate for months on a single battery. Neuromorphic chips allow us to push high-level intelligence to the extreme edge. Because these chips process information temporally, meaning they understand time as a fundamental variable, they are exceptionally good at pattern recognition, sensory processing, and anomaly detection. A neuromorphic system doesn't just see a frame of video, it feels the movement of pixels over time, much like the human retina. This makes it the ideal substrate for the next generation of autonomous hardware that must react to the physical world in real time with near-zero latency. Deeply and honestly, we must acknowledge the software gap that currently hinders neuromorphic adoption. We have spent 70 years learning how to write code for von Neumann machines. We understand loops, variables, and sequential logic. Neuromorphic systems require a completely different paradigm: asynchronous, parallel, and probabilistic. You don't program a neuromorphic chip in the traditional sense. You define the topology of synaptic weights and the dynamics of the neurons. This requires a new class of software engineers and DevOps pipelines that can handle the training and deployment of spiking neural networks. We are effectively moving from the era of deterministic software to the era of biological computation. This is a massive shift, but it is a necessary one if we want to move beyond the power-hungry constraints of modern silicon. In the context of your work with hardware research and development, neuromorphic computing offers a path to truly stealth and autonomous operations. Imagine a sensor package that can listen for specific acoustic signatures of machinery or vehicles, remaining in a deep sleep state until the exact pattern is detected, then processing that information locally without ever needing to ping a cloud server. This level of autonomy and low power efficiency is only possible with neuromorphic architecture. We are building the digital cerebellum, the part of the machine that handles the complex real-time interactions with the physical world so that the higher-level logic can focus on the mission goals. This is the convergence of biology and silicon, and it is the only way we will ever build machines that can truly think and act as efficiently as a living organism. To dive further into the physics, we must look at the role of memristors in the neuromorphic future. A memristor, memory resistor, is a passive circuit element that remembers the amount of charge that has passed through it by changing its resistance. This is the perfect hardware analog for a biological synapse. By integrating memristor arrays with standard CMOS logic, we can create non-volatile neural networks that don't lose their state when the power is cut. This removes the need for a separate hard drive, or SSD, for the neural weights, further collapsing the distance between data and processing. This in-memory computing is the final nail in the coffin for the von Neumann bottleneck. We are moving toward a world where the hardware is the model and the model is the hardware. Geopolitically, the race for neuromorphic dominance is a race for cognitive sovereignty. The ability to deploy high-level intelligence without reliance on massive power grids or cloud infrastructure is a strategic advantage that cannot be overstated. From satellite-based image analysis to robotic search and rescue in disaster zones, the the efficiency of the neuromorphic chip will be the deciding factor in mission success. As we scale this technology, we are also looking at plasticity, the ability of the chip to learn and adapt its own hardware structure based on the data it receives. This on-chip learning means that a device deployed in the field can get smarter over time without needing a firmware update from a central server. It is the ultimate expression of decentralized intelligence. In conclusion, neuromorphic computing is the architectural manifestation of our desire to merge the speed of silicon with the efficiency of biology. It is a refusal to accept the limitations of the past and a commitment to building a more intelligent, responsive, and sustainable future. By harnessing the spiking nature of information and the physical properties of memristor materials, we are creating the brain of the future. The era of the biological machine has begun. And the potential for what we can build on this substrate is limited only by our understanding of the very mind we are trying to replicate.